Hi everyone, welcome to CHEM. Now today's video is on Chemical Kinetics Part 9 video, and here we are going to deal with application of steady state approximation. Now before starting, already 8 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So in the previous video we had already dealt with steady state approximation. So what was it? When we have a short-lived species in a consequent reaction or sequential reaction, then the derivative of its concentration is equal to 0, and this will help us to get the rate constant and the rate law. Now this is applicable only for short-lived species, and concentration of the intermediate is constant and is very small, and thus intermediate is very reactive, right? Now we have to know the steps to apply a steady state approximation in a particular sequential reaction. So first we have to look for the reactive species which is short-lived. Next we have to write down the differential form of rate equation as we have done previously, right? Next we have to write this one, that is d concentration dt equals to 0, and then find out it in terms of stable species. Then we have to substitute the concentration of intermediate into the rate equation. So first we will take an example and then understand what is going on. So first our example is this one. See, we have a reaction like this, that is R1 plus R2. Reversible reaction, this is K1 and this is K2 and this is the intermediate I. Then I will undergo further reaction K3 as rate constant to form product P. So we have the short-lived species as I. Now we have to write down the rate laws. R1 equals to K1, R1 concentration and R2 concentration, right? Next we have R2 where it is equals to K2 I concentration, okay, and R3 equals to K3 I. Now we will write down the differential of I, that is di by dt. This is equal to rate 1, that is, since there is a formation, minus R2 because there is a disappearance of I, again minus R3 because again disappearance of I, right? Now we have to apply steady state approximation. So we will apply steady state approximation. And what is it? That di by dt will be equals to 0, right? So ultimately what we get is like this, 0, and we know what is value of R1, that is K1, R1 concentration, R2 concentration minus K2I minus K3I. Now we need the value of concentration of I in form of stabler state. So on further simplification we get concentration of I equals to K1 R1 R2 divided by K2 plus K3. Now what is the formation differential of dP by dt? It is equals to K3I, right? So we will just substitute the value of K3. So we get K3, K1, R1, R2 by K2 plus K3. Now see here, all these factors are actually a constant. So finally we can write it down as K R1, R2 concentration. So rate of formation of product we have obtained as dP dt, right? So overall rate of formation of product is 1 with respect to each species. For R1 also 1, for R2 also it is 1. Now we have another problem. So now previously we had dealt with a virtual situation, right? Where we had imagined different R1 and R2 and then P. But here we will take a question and try to answer this. So this is problem 1. 2 NO plus 2 hydrogen it produces nitrogen plus 2 water and the rate constant is K. And for this reaction there is a mechanism which is being proposed. So NO plus NO produces N2O2, K1 and K minus 1. Similarly, N2O2 plus hydrogen produces N2O plus H2O. N2O plus hydrogen produces our N2 plus H2O. We have to show that rate of formation of nitrogen obey third order kinetics under the condition where we can see K minus 1 is much greater than K2. So what is the intermediate? In this case there is two intermediates. One is N2O2 and another is N2O. So we have to do two steps, right? So let us do. First we have to write down the rate equations. So R1 equals to K1 NO square because two molecules required. R minus 1 equals to K minus 1 into O2, right? Now we have to write down R3 and R2. So R2 is equals to K2 into O2 and hydrogen, right? And the last one, which is R3, is equals to K3 N2O and H2. So we have obtained the 4 rate laws. Now we have to come and obtain the dN2 dt. We have been asked to get the value of dN2 dt. What is its value? K3 N2O concentration and hydrogen concentration, right? But we do not know the value of N2O. So first we have to undergo steady state approximation. So first we will find out for dN2O2 by dt. This will be equals to R1 minus R minus 1 minus R2. And this comes to be as K1 NO concentration square minus K minus 1 N2O2 minus K2 N2O2 and hydrogen concentration, right? And again for the next step we will apply steady state approximation. Apply SSA. So this part will become 0. 0 equals to K1 NO square minus K minus 1 N2O2 minus K2 N2O2 and hydrogen, right? So ultimately we get the value of N2O2 equals to K1 NO square by K minus 1 plus K2 hydrogen concentration. Now we will come for d N2O by dt. This is equals to R2 minus R3 and we can write it down as equals to 0 by applying steady state approximation. Write it down by applying SSA, that is steady state approximation, and here will be K2 N2O2 H2 minus K3N2O and hydrogen. Okay. Ultimately, what we get as concentration of N2O is equals to K2 N2O2 hydrogen by K3 hydrogen. And if you observe here carefully, what will happen? This hydrogen and this hydrogen will be gone. So we are left with K2 by K3 N2O2. And we have already obtained the value of N2O2, right? So we will substitute all these values together. So for dN2 dt, we have, it is K3 N2O and hydrogen, right? So from here we can write its value as K3 into K2 by K3 N2O2 into H2, right? So this K3 and K3 gets cancelled. What we are left with is K2 N2O2 and hydrogen. What is the value of N2O2? We had already come across, that is this one, right? So we will just substitute this value in the next step. It will be equals to K2 H2 concentration K1 NO whole square by K minus 1 plus K2 hydrogen. This will be equals to K1 K2 H2 concentration and NO square concentration. Now remember what we had seen in the problem. We had seen that K minus 1 is much greater than K2. So here the value of K minus 1 is much greater than this one. So we can write it as divided by K minus 1 only. So ultimately what we get is that this is a constant part. So this can be taken as K, right? And the other part can be written as H2 and NO concentration square. So from here only we can see that 1 here and 2 here. So it is a third order kinetics, right? Thus it is proved. So these are the different types of sums which can come from steady state approximation. Now listen very carefully. I will provide you with the checkpoint in the description. You can check it out, the PDF file. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.